All right, hello, this is your Unit 11 study guide. I put a little recap of everything on here. I'm just going to talk about it real quick. I would look at the nth term test first. I think that's easiest. If the limit to infinity goes to anything in the world other than 0, then diverges. And then look for one of the special ones. And you can do these in whatever order you want. When I go through and do them, I'm going to kind of like, I would go through and look for all of the geometric ones and then look for all the P series ones. And is it telescoping? Is it alternating? So look for all those kind of special ones first. If it's not any of those, and you're down to these ones that are a little bit more work. These are all fairly quick. These are the ones that are going to be a little bit more work to them. If it's something you can easily integrate, do the integral test. If you can easily compare it to another series, like you can compare it to something that's geometric or a P series, then do a comparison test. I would always do limit comparison. I think trying to prove which series is smaller or larger than the other is a bit more of a headache. That's my personal opinion. So for all these, I'm going to do limit comparison. If I do a comparison, it's kind of up to you. If none of that works, you'll need to do the ratio test, which is the one that's the most work. So kind of like use that as a last resort. On these first three, I'm telling you that they're geometric. So you don't have to say that they're geometric because I'm telling you that they are. So if it converges, find the sum. If not, you're just going to say it diverges and why. So for this one, our R value is -1/6. That absolute value is smaller than 1. So if R is smaller than 1, it's going to converge. And so we're going to actually get the answer. So it'll be 4/1 minus -6. So negatives will cancel. It'll be +6. And I am asking you to simplify it. So we need to go through the algebra. So that'll be 4 over, let's see, that'll be 7/6. And that would be 4 times 6/7. So that would be 24/7. If I can put that in here. So 24/7 for that one. This one doesn't look geometric at first glance, like it doesn't follow that pattern, A times R to the N. But if you list out the first few terms, then you'll be able to see it. And I'm telling you it's geometric, so we know it is. So if we start with 0, if you plug in 0, you're going to get 2/1, which would just be 2. If you plug in 1, you're going to get 4/3. If you plug in 2, you're going to get 8/9. And you can keep going, but usually like 3 or 4 terms is good enough to see the pattern. So our first term is 2, and we're multiplying by 2/3 each time. So since 2/3 is smaller than 1, this is going to converge. And so we're going to do the same thing we did for question 1, actually get the answer. So 2/1 minus 2/3. So that would be 2/1/3. That would be 2 times 3, so 6. All right, and then this one, our first term is 1, and we're multiplying by 5/2 each time. 5/2 is bigger than 1, so this is going to diverge. So we're going to say diverges because R equals 5/2, and that is bigger than 1. All right, now this next section, this like 4 through 18 here, I would do these in this order. Like I would look for ones where you could use the nth term test. Now to make the video not take forever, I kind of wrote myself a note like what order I'm going to do these in. On the test, obviously, it'll take you a little bit longer because you're going to have to read through every one of them. But first, I'm going to go through and find all the ones I could do the nth term test for. So if the limit goes to anything other than 0. So if we look at number 4, if you do limit as n goes to infinity of this, you have e to the n in the numerator, that's going to get infinitely large. So this is going to go to infinity. And so we'll say diverges by the nth term test. And then another one we can use the nth term test for is number 8. So if you do limit as n goes to infinity of n over n minus 7. They're both n, that's a tie, so we're going to use the leading coefficients. It would be 1/1, which is 1. And again, if it comes out to anything other than 0, it's going to diverge. All right, then I would look for ones that are geometric. So number 6 is geometric. The first term is 2, the R value is 7/9. That's smaller than 1, so it's going to converge. So converges because series is geometric and r equals 7/9, which is smaller than 1. In this case, you do have to mention that it's geometric. For these first three, you didn't because I said that in the directions. Here, where they're all mixed up, you're going to have to say that it's geometric if that's what you're using as your explanation. All right, then I would look for ones that are a p-series. So number 10 is a p-series. We have 1 over square root of n. That means p is a half. For square roots, that would be a half. And remember, these are opposite, the geometric ones. P needs to be bigger than 1 to converge. So if p is a half, then that is not going to converge. So we are going to say diverges because series is p-series and p equals a half, which is smaller than 1. So pretty much the same thing we wrote for this one, except instead of geometric, we said p-series, and it's the other way around. P has to be bigger than 1 to converge. And then there's one more on here that is a p-series, which is number 17. In this case, p is 4, so this one's going to converge. So converges because series is p-series and p equals 4, which is bigger than 1. All right, so next thing on the list that I would want to look for is if it's telescoping. Those don't show up real often. I just threw one of them on here, and it is number 13. So what happens is when you list out the terms, you get stuck with this first part, and then the second part will cancel with the first part of the next one, and then that will cancel with the first part of the next one. So as long as your limit to infinity for this second part is a finite number, then it's going to converge. And usually it's 0 most of the time. And that'll be the case here. As n goes to infinity, the denominator is going to keep getting larger and larger. So that is going to go to 0. So it is going to converge. So I'm going to say converges because series is telescoping. And it's all these special ones like geometric p-series, telescoping, alternate series. You have to mention that because that's what you're using, as your explanation. So it converges because the series is telescoping and this limit is finite. Because if that kept getting bigger and bigger and bigger, it wouldn't converge anywhere. But as long as that part's finite, and again, usually it's 0, then it's going to converge. All right, so now we're looking for any of them that are alternating. So if there's a piece in there that has a -1 to the n or a -1 to the n plus 1, that's what's going to cause it to alternate. So if you look at number 5, this one is alternating. So we're going to do the alternating series test. So first we're going to do limit as n goes to infinity of this part. And you don't need the fact that it's alternating. You can just put 1 there. So 1 over n plus 1. That is going to go to 0. So that's the first part of the test. That needs to go to 0. And also the terms need to always be decreasing. So if you plug in n plus 1, so that'll give you n plus 1 plus 1. That would be n plus 2. That needs to be smaller than 1 over n plus 1, which it would be. If you have a bigger denominator, that's the smaller fraction. So this converges. Oh, I guess I should say that is true for n bigger than 1. So this converges by the alternating series test. And you can abbreviate that AST, so alternating series test. And then I think I had one more, I wrote it down, which is the other one. Number 14 is alternating. So you see that -1 to the n plus 1 in there. So same thing, we're going to do limit as n goes to infinity of 1 over n plus 1, that's going to go to 0. And again, if you plug in n plus 1, I made this one is almost the exact same thing. The alternating series ones do turn out a lot the same. And so this one converges by alternating series test. All right, so unfortunately, that is the end of like the kind of simple ones. The rest of these are going to be a little bit more work, so I'm probably going to need a scratch piece of paper for these. Let's go through and find any that we could easily integrate. Let's see. which ones we could actually do a nice integral of. Not any of those. Oh, this one we could do an integral of. So let's do number 12 using an integral test. I'm going to do limit as b goes to infinity, integral 1 to b, and then I'm just going to change the n's to x's. Oops, that's a squared. All right, and so this is going to need a u substitution. We'll do u equals x cubed. Du would be 3x squared, and I'll need to adjust it with a 1/3. So whenever I do the substitution, I kind of don't write the limit because I'll bring it back just for the sake of simplifying things here. So I'm substituting in the x squared dx. And so what's still there is 1 over e to the u. That would be e to the negative u. So that antiderivative would be negative e to the negative u. So I'll bring the limit back. This is negative 1/3 e to the negative x cubed such that 1 to b. And so we're going to do upper boundary minus lower boundary, and then we will evaluate the limit. That's like your last step, see what it comes out to. So if we plug in b, let me write this as a fraction. It would be negative 1 over 3 e to the power b cubed. Sorry, that's a 3 in there, it got kind of small. And if we plug in 1, we'll have negative 1 over 3e. If you plug in 1, 1 cubed is still 1. It would just be e to the first there. Now we're going to evaluate the limit. So as b gets larger and larger and larger, this part's going to go to 0. These negatives cancel. And so we got a result. We got 1 over 3e. So it didn't go to infinity. Like we got an answer. And so that means that the series also converges. So this converges by the integral test. So again, if it came out to like infinity or something, then we would say diverges by the integral test. So whatever the integral does, the series is going to do as well. All right, and then let's see if there's another one we can integrate. Number 15, we're going to be able to integrate pretty easily. So we're going to do limit as b goes to infinity, integral from, oh, this one's 2 to b. That's not going to make a difference. ln of x over x dx. We're just trying to see if it converges. We're not trying to actually get the answer. It's just, does it converge or does it diverge? So we're going to let u equal ln of x. Du would be 1 over x dx. There's no adjustment we need to make there. The x in the denominator and the dx are what we're substituting out. So this would be integral of, I guess the only thing left is u, du. There's not really much to that. So antiderivative of that would be 1/2 u squared. So 1/2 ln of x squared such that 2 to b. And then we're going to do upper boundary minus lower boundary. So if you plug in b, that'll be 1/2 ln of b squared. And if you plug in 2, 1/2 ln of 2 squared. And then the last step is to evaluate the limit. Now, as this goes to infinity, this is going to keep getting larger and larger and larger and larger. So this is going to go to infinity. And so the series, since the integral diverged, then the series is also going to diverge. So this is diverges by the integral test. All right, let's see if there are any that we can easily compare to another series. And you would want to compare them to a geometric or a p series because those are the two like easiest ones to use. So let's see which ones we can compare. All right, so looking at number 7, sorry, I have to pull the paper over here so I can the new space to write. So looking at number 7, I'm going to compare this to the series 4 over n cubed. So I'm just leaving off that +1. So that's a p series where p is 3. So this one's going to converge. So that converges because series is a p series. and P equals 3, which is bigger than 1. So what we're trying to say is because this one converged, this one's going to converge as well. If you want to use limit comparison, you're going to do limit as n goes to infinity of, and it doesn't matter which way you do this, but one of these over the other one. And as long as that comes out to a finite number, then whatever one of them does, the other one is going to do as well. So this would be 4 over n cubed plus 1 times, then we're going to reciprocate this, n cubed over 4. 4s are going to cancel. We have an n cubed over an n cubed, that's a tie, so you would use the leading coefficients, which would be 1 over 1, which is 1. That's a finite number. So since this one converged, this one does too. So we're going to say converges by limit comparison. All right, so let's see another one that we can compare. Let's look at number 9. I think I'll have enough space on this side of the paper. All right, so number 9, I'm going to compare that to 3 over 2 to the n, just leaving off that minus 2n. This is the most important part of it, like the part that's sort of in control there, so I'm just leaving that off. This is geometric. Let me just rewrite it again so you can see it with the pattern a little bit better. It's 3 and then times 1/2 to the n. So a is 3, r is 1/2. So this is going to converge because the series is geometric and r equals 1/2, which is smaller than 1. So again, what we're trying to say is because the one we're comparing it to converged, this one's also going to converge. We just have to show that this limit comes out to a finite number. And again, it doesn't matter which one goes over which, because you're going to end up reciprocating it anyway. I always write out that first step, but honestly, if you wanted to skip that and jump straight to this step, because you know it's going to flip over, then you can. These 3s are going to cancel. Just the same in the other one. It's basically just a lot of writing to show that. But again, you get 2 to the n and 2 to the n. It's a tie, so you're going to use the coefficients. It's going to come out to be 1. And since that's a finite number, since this one converged, this one does too. If this one had diverged, we would say this one does too. They're going to do the same thing as each other. It's kind of like the integral test. So it converges by limit comparison. All right, and then I don't want to compare that to anything. Let's see. Number 18, we can do a comparison pretty easily. So we're going to compare this to 8 over square root of n to the 5th. So I'm just leaving off that plus 6. You're just basically taking the most important part of it. So this is a p series. P would be 5/2. If it's a square root, it would be 1/2. There's just a 5 there. So 5/2. That is bigger than 1. So it is going to converge. So converges because series is a p series. And p equals 5/2, which is bigger than 1. So again, what we're trying to say is because this one converged, this one does too. We just have to show this limit. I wrote that kind of quick. It's the same as the other 2 we just did. That's all. And again, if you want to skip this step, you can and just jump straight here. So again, we, n to the 5/2 and n to the 5/2, it's ties. So we're going to use the coefficients. They're both 1, so it comes out to 1. So converges again by limit comparison. All right, Now we're to the end of our list. I have nothing left for these last two, so we're going to have to do a ratio test, which is actually not that different from the limit comparison that we were just doing. It's just sometimes they get a little bit messier because, like, I mean, look at it, kind of complicated. But stuff's going to cancel, and as long as the limit comes out to something smaller than 1, it's going to converge. If it comes out to bigger than 1, then it's going to diverge. All right, so for 11, we're going to do ratio tests. So limit as n goes to infinity, big absolute value. We're going to plug in n plus 1 everywhere we see an n. And then that's going to go over the series itself. And so again, if you are comfortable skipping that step, you can do that. I always write it out because it helps me to see it. But again, what's going to happen is we're going to flip this. So in the numerator, we've got 5 to the power n plus 1 times n plus 1. And then this n factorial is going to go up there. Everything else is in the denominator. But what you want to kind of do is line them up. Like I'm going to put the 5 to the n next, and then times n, and then times the n plus 1 factorial. And I wrote that really big. Usually I have enough space to keep going, but I don't. I'm going to come down to the next line. All right, so now we're looking for some stuff to cancel out. This would be 5 times 5 times 5 times 5 times 5, n plus 1 times. This would be 5 times 5 times 5 times 5 times 5, just n times. So all the 5s would cancel except one of them. You'll have it left in the numerator. I can't really do anything with this, so I'm going to keep that n plus 1 and that n. And then a similar thing is going to happen with these as they did with the 5s. Everything in your list of numbers is going to cancel except for that n plus 1. All right, so we get these n plus 1s now that cancel, and now I'm going to do the limit. As n goes to infinity, this is going to get bigger and bigger and bigger and bigger. So this is going to go to 0, which is smaller than 1. So this converges by the ratio test. Again, as long as that limit comes out to something smaller than 1, it's going to converge. Bigger than 1, it's going to diverge. All right, and then number 16. So same thing, we're going to plug in n plus 1 and then put that over what's there. And so again, this is going to reciprocate. So in the numerator, we're going to have n plus 1 squared. This 3 to the n is going to come up there. Denominator is everything else. But again, try to line it up. Like I'm going to put the n squared first, and then the 3 to the n plus 1 after that. And so now we're looking for some stuff to cancel out. I can't really do much with the n plus 1 squared and the n squared. But here, all the 3s are going to cancel out except for one of them. So we'll just have a 3 left there. So let's see, this would be, if I multiplied this out, I would have an n squared. This would be a 3n squared. So if you think about having an n squared over a 3n squared, it's a tie. You would use the leading coefficients. And so that limit would go to 1/3, which is smaller than 1. And so this one also converges. So converges by ratio test. All right, so then these last two. So number 19, converges absolutely, converges conditionally, or diverges. So first we want to look at what the absolute value of this would be. And what that's going to do is just cause it to not be alternating. All the terms would be positive, so just be 1 over n squared. So if this converges, it converges absolutely. If the absolute value diverges, then you would check the series itself, and if that converges, it would converge conditionally. If both of them diverge, then it just diverges. This is going to converge because it is a p series, and p is 2, which is bigger than 1. So it converges because series is p series. and P equals 2, which is bigger than 1. So since the absolute value converged, we're going to say converges absolutely. But again, if this diverged, then we would have to check this series itself, the alternating one, and see what that did. So, you know, just for the sake of being thorough, since this is the test review, I'll just do that anyway. Pretend that we got that this diverged. Then you would have to go back and check the original series. So I'll just do that anyhow. It's only going to take me a second. This is alternating. So we would do the alternating series test. You would do limit as n goes to infinity of that. That's going to go to 0. And then if you plug in n plus 1, that has to be less than just with n. And that would be true because, again, the bigger denominator is going to be the smaller fraction. So we would say converges by the alternating series test. So again, pretend this one diverged. If you get that this one does converge, then you would say converges conditional. All right, and then for number 20, we're doing that error bound with the remainder. Approximate the sum of that series using the first 4 terms. All right, so first we have to list out the first 4 terms. And this is the one question on the test you're going to get a calculator for, so that you can type in all those fractions. You can just put a decimal for it. So let's get the first 4 terms. So plugging in 1 plus 1 is 2. That would make this positive. And then down here, you just have 1 squared, which is 1. So let me just write 1 for that. All right, and then if you plug in 2, this is going to be odd, so it'll be negative. So negative 1/4. And then the third term would be positive 1/9. And then we'll have minus 1/16. So let me type that in and see what I get for that. And so that I don't have to round off a decimal, I turned it back into a fraction. So I got 115 over 144. Just again, because I don't want to round or truncate the decimal. This is like a perfect answer where I didn't like chop off the decimal. All right, so the sum of the series, we're approximating it using this. So the sum of the series, this absolute value of this, minus our 115 over 144, that will be less than, or just less than or equal to, I don't really mind what you put there, but less than or equal to the 5th term. So we're using the first 4 terms. The error is going to be less than the 5th term. So it's always less than, it's like saying your amount that you're off by is going to be smaller than whatever the next term is. So the 5th term, so if we plug in 5, we're going to get 1/25 for our 5th term, like if you catch the series going. And then we're just going to solve that. So an absolute value is going to split. We're going to have s minus 115 over 144 is less than or equal to 1/25. Oops. And greater than or equal to negative 1/25. And again, I'm just going to put this in the calculator. And I'll use a decimal for this one. All right, so this one's the smaller one. When I typed that one in, I got 0.758. And then this one's going to be the bigger one. When I typed that one in, I got 0.838. So we know that the sum of the series would be somewhere in between those, which is pretty accurate. You know, and the more terms you use, the more accurate it would get, because these terms are going to keep getting smaller and smaller. And so your error would keep on getting smaller and smaller. But the sum of the series would be somewhere in between those 2 decimals.